afternoon, everyone. Thank you for attending to this presentation. As you will see, Dan is a great presenter. He's doing a very interesting work at the National Renewable Energy Lab, and I have asked him to tell us a little bit of his background so that we have an idea of how he ended up in the job and doing what he has and doing what he does. So again, to the people that are connected remotely, if you could please turn on your microphones, because if you make a sound, the screen will switch to you. And now we are recording this, and it will be posted in our website a week after this presentation. So welcome, Dan. Thank you so much for being with us. And if you could please tell us a little bit about your background before you start with the details.
Yeah, sure. So I am Dan Getman. I am the Geospatial Data Science Team Lead at the National Renewable Energy Laboratory. And I'm here to give a presentation that I gave at FOSS4G, maybe a slightly different version of that, but just to talk a little bit about open source tools in spatial analysis. But as Raphael asked me to give a little bit of background, I have an undergraduate degree that is in geography and computer science, and then a master's degree in remote sensing, which I've done almost none of in my professional career. I started out after school working for an environmental engineering company doing very traditional geospatial analysis for them. Once someone knows that you know how to program, that's really what they want you to do. And so I wound up doing a lot of writing code that actually does spatial analysis, and then writing code that does visualization, and then writing code that does analysis and data management and visualization in web-based GIS back in the late 90s, early 2000s. So environmental engineering, I worked for Department of Defense as a contractor out in Virginia for a little while. I worked at Oak Ridge National Laboratory for 5 years doing data science work there. And I've been at the National Renewable Energy Lab for about the last 5 years, doing a wide variety of visualization work, analysis work, and project management work. When you get old, they want you to manage projects, is basically what it boils down to. So if you're not familiar with the National Labs, the National Labs are a really interesting place. What we do is we solve really hard problems for the government, and that winds up going to industry. And so many of the things that have happened at the National Labs have wound up going directly to industry. But the reason it's interesting is because you get funded from every agency in the government: Department of Defense, Department of Energy, Homeland Security, and you also get funding from external agencies, and you also get funding from industry. And all of this funding that you propose work and it comes to you once they decide that it's a good idea, that goes towards doing research, like actual research that you can write papers on. Tons and tons of papers come out of the National Labs. But the thing that's really interesting about it is that it's not always about writing papers. And in fact, most of the time it's about developing something very practical that solves a really practical problem in either government or industry to help push renewable energy forward. And so when you think about what the National Labs are, they're this really interesting mix between academia and industry. And I like to think of it as academia and industry coming together to make a beautiful unicorn that is the National Labs, right? And so the National Renewable Energy Lab is kind of a small lab compared to some of the other labs. We're about 2,400 people. The other labs are in the thousands and thousands of people, like 10,000, 12,000 people in some of the other labs. But we're about 2,400 people, and all of those people are focused on one goal. And the goal of the lab at the National Renewable Energy Lab is how do you figure out energy efficiency and renewable energy in a way that's sustainable, so that in 20 years from now, we're looking back on all the decisions we're making now and saying, man, I'm really glad we did it that way. That was the right way to do it. How do you make sure that the technology is the best technology we have? How do you make sure it's used in the right places, in the right ways, the right combinations? That's the work we do. And so it's everything from physics to bioenergy, wet science, mechanical engineering, and analysis. And my team is focused in the analysis group. And so we're about 14 or 15 people, depending on how many contractors and interns we're currently abusing. John can tell you that story. But we are very much focused on doing spatial analysis in the renewable energy domain. So that's traditional GIS, what you learn in your first 2 classes, where you're overlaying data and figuring out where the intersections are and saying, yes, it doesn't make sense to put PV in a swamp. Great, we've got that choice. Right, so we do traditional GIS, which I think of as like site selection and things like that. But we also do what I think of as big data analysis or data mining or spatial statistical analysis, where we're doing things like taking an enormous solar resource data set that's got billions of values over every half an hour, over hundreds of thousands of grid cells across the United States over 10 years. And we compare it to another solar resource data set that has the exact same data or type of data, but they're different. They come from a different data provider. And so how are those different? Where are they different? What makes them different in the modeling that we do? And so those are really complex problems that wind up being spatial temporal statistical problems. We also look at PV adoption across the United States, and why is adoption happening in certain areas and not others, and what factors contribute to that, and how is that related to climate data and economic data and socioeconomic data. We do spatial temporal data visualization, which is one of the things I'll probably be focusing on a little bit in this presentation. And then we do spatial application development, which is another thing I'll talk about in this presentation. But again, you know, the point to all of this, it's really fun and interesting and technically challenging, and I enjoy it tremendously, but it's really all focused on making good decisions. How do you make sure that you've got the right information to make a good decision? And there's a lot of theoretical stuff that happens out there, and all the things that we're doing aren't. They're focused on very practical outcomes. I also wanted to be clear, 2,400 people at the lab, there's something like 18 or 19 labs, there's thousands and thousands of people in this industry, and I'm talking about 14 of them. I'm talking about my group and what we do and how we do analysis. It's spread out very differently across the labs and even differently at NREL, and so I just wanted to clarify that. I'm talking about me and my team. So what am I talking about with me and my team? We are looking at a team that 5 years ago was making maps for people. That's what we were doing. We had ArcMap, and we had a bunch of data that we had in shapefiles and raster data sets, and we used Esri products to do analysis and turn them into maps. Make PDFs, make reports, tell you where the most appropriate, you know, place for certain technologies was going to go, but it was all really rooted in traditional GIS. And what we've done over the last 5 years is we've completely transitioned. Almost nobody on my team uses Esri products or really any other proprietary product except for Adobe Illustrator. And so in the light of thinking about how does Phosphor-G work in research and in industry, Rafa and I were talking about that, how to present something like that, how to talk about that transition that we've made. And so what I want to talk about is, what does that mean for the team? You know, how do we decide to do it? What's it meant for the team? What are the good and bad outcomes of being in that situation? And what do we do with all of this technology anyway? And so this is where we were about 5 years ago. You know, you had ArcMap on a laptop, and you got a bunch of shapefiles and some Excel spreadsheets, and you turned that into data that you could use, and you did really, and I don't want to downplay this, excellent analysis has been happening using those tools, right? And that's what we did. But that's how it was set up. Everyone had their own computer. Everyone had their own data. We replicated data all over the place. It was kind of cowboy land for traditional analysis. And when you think about the big analysis, the solar resource data, the wind resource, you know, I think about the loving relationship between a man and his C code. And that is what it was getting a bunch of spreadsheets and CSVs and text files and turning those into solar resource data sets that really only existed in someone's C code. And then it would dump out a whole bunch of other binary files or text files that represented all the data, right? Great analysis, really interesting outcomes, but the methodology and the data management and the code management were in this sort of way. Terabytes of data, I guess I should point out. These are not small data sets. These are enormous data sets that we deal with, in some case petabytes of data. So then something really interesting and magical happened on the team. 3 people came in, and I was one of those people, who had focused for the last few years on doing application development. The application development was focused on how do you allow people to interact with spatial data in a way that lets them understand it, do analysis, look at complex data sets, right? This isn't, you know, the out-of-the-box Esri stuff that pops open and you've got a layer tree and you can turn things on and turn things off. This is actually running models and things like that. And so the thing that was really interesting about this, again, it's 5 years ago, but we brought to the team the fact that we were using Postgres, the fact that we were using Subversion for version management of the data and of the code. And the fact that we were using something called EXTJS, which most of you guys probably haven't heard about. But if you know anything about modern web development, we've gone from animated GIFs on everyone's homepages to these frameworks for building web applications, right? So you can make a web application that's just your own code, and you code it. But what these things do, EXTJS is one of the early ones, used to be open source, and now you have to pay for licenses in some circumstances. But Ember and Angular and Rails and all these other things you're hearing about, what they do is they organize the process of going from data in a database to data on a web page. They don't do it all for you, but they really clearly define what objects are and how event management happens and how the visualization works with the objects which work with the database. And so this organizational structure didn't really exist in our analysis. Utilization of a database didn't really exist in our analysis. And taking code and putting it in a repository didn't really exist in our analysis. And so as the spatial application developers or spatial temporal visualization people, in bringing this to the team, we brought all of these capabilities to the team that they weren't really aware of in the past. And so that fundamentally, over the course of the last 5 years, fundamentally changed the way we do analysis because, and this is sort of the key point, because we went from using a lot of traditional proprietary tools to using a lot of open source tools. And by interacting with the analyst and the people doing application development and the people doing visualization, there was a huge amount of cross-pollination. And that's really what I want to try to describe in the partially true, almost where I want it to be outline that I'm just about to show you. So before, what we were doing, and I want to walk around and point, and I'm trying to stay in front of the camera. So before, what we would do is we would take these data, we would turn them into shapefiles, right? That would be the first thing you'd do. And what we do now is any data that we get, even if it's a shapefile or a spreadsheet or whatever it is, we immediately load it into one of two formats. It's either going into Postgres/PostGIS, or it's going into HDF. And if you're not familiar with HDF, it is another magical unicorn. And that, so I'm going to digress for just a moment to talk about this. HDF is like an open standard, but the software that we use to deal with it is also open source. So I think it sort of fits in. The interesting thing about these two formats in particular is one of the massive limitations to using Esri products is you can't use big data in them. I mean, you run out of space so fast in what you can open and deal with that once you get past, looking at these sort of low-res national data sets or high-res, really local data sets, you run into a place where you can't really do anything with them. And so Postgres, you can load billions and billions of values in, millions and millions of rows of data, and do spatial analysis on it, and it's fast. And HDF is the same thing, but for data that's an order of magnitude bigger. So for these terabytes and terabytes of solar resource data and wind resource data and things like that, HDF is a format that allows you to have literally a 40 terabyte file, and you can open it and search it and find 10 gigabytes in it and just extract it out and use it like that. It's very, very, very fast, much faster than a database for these big data sets. And so these are the two formats we put it in, pretty much regardless of what we're doing with it. That's where we start. And then when we do analysis on it, we use Q sometimes. Usually what we use Q for is visualization. Like if you've got data in Postgres, you need to look at it, Q is a great way to do that. Most of the analysis, if not all the analysis we do, is in Python and R. And so Python is a programming language. You guys are probably all familiar with it. It's the scripting language that Esri uses. We're talking about Python that's just by itself. We use NumPy and SciPy and the different visualization libraries that are available. We use IPython Notebook. But these are, pretty straightforward Python to do spatial analysis, because all of the things that you can do in ArcMap, and even in Python using ArcPy, you can also do using other libraries using Python and make it significantly faster and be able to deal with larger data sets. And R is the same way. If you're not familiar with it, R is a statistics package. It's like SAS or something like that. It's kind of MATLAB sort of a thing. It's designed to do math. It's not designed to do programming. But it's a scripting language that you can use to do a tremendous amount of spatial analysis. And most of the spatial statistical analysis we do in R. And then we do use Esri for certain things. There are staff members who really are comfortable with it. It's actually, from my perspective, one of the best packages for doing raster analysis. And so we still use it for that. Postgres is almost at a point where it's kind of the preferred tool for that. Not quite. And I put the little funky cat octopus GitHub symbol there because all of the code that we do, so this is one of the things I think that's critical as someone who's getting started in analysis. Put your code in GitHub. Just get it. It's free. Take a day and learn how to use it, and you will always have your code no matter what you do. It'll always be saved. You'll always have the version you had 2 weeks ago. The reason I put this here is to demonstrate that all of the analysis we do, whatever software it's in, all of the files we save in GitHub so that we always have it. If someone wins the lottery or whatever, then we have all of their analysis. The other interesting thing about this slide is you can see that arrow going back. So you get some data, population data, census data, energy, statistics, whatever it is. You do some analysis on it, and then your analysis is automatically loaded back into the database, right? So what you do when you use Postgres as a database for analysis is you create new tables from the results, and then the data that is resultant of your analysis is then available for everyone else who's doing analysis, right? So the end result is in an accessible format already, if that makes sense, which to me is one of the other magical things about using a database for analysis. We do use Adobe Illustrator as a proprietary piece of software, but the reason we do is because we make like National Geographic quality cartographic products. We have 1 or 2 staff members who specialize in that, and quite frankly, it's the best tool out there for doing that, and so that's the one we use. If you've seen Adobe Illustrator and Avenza, if anybody's interested in like really cool cartographic products, look up Adobe Illustrator and Avenza, because you can just bring shape files in and do things with them. It's very powerful for producing maps that tell stories, maps that are easy to interpret and give you a feeling of what the data is trying to tell you. That's what we wind up doing in the end. So everything kind of scooched over there. And this is where it gets, oh, I guess I'm cut off on the other side. Sorry about that. This is where it gets really interesting. So the data that we do analysis on and the data that we use in decision-making and writing reports and things like that that we deliver to DOE is also data that a lot of other people are interested in. And so what we've done is we've, again, in the vein of making spatial application development work, we've had to make web services work. And if you're not familiar with web services, it's basically you can hit a URL with a couple of parameters and say, give me all the data, and all the data comes to you, right? It's very, very easy to use these things to pull in census data and other data sets. We have solar resource data, wind resource data, electricity rates, things like that you can just pull off of these APIs that are available through Ruby on Rails, which is an open source framework for doing that. So one of the things that I think is interesting about this from an open source perspective is we built developer.nrel.gov, which is where all of these web services are available at. And not only can you pull raw data, but you can run models. And so we have a model that if you tell it, I've got a PV system, it's a certain size and a certain place, and it's got a certain tilt and azimuth and all the other specs, it'll actually tell you what that system will output every month for a whole year, every hour for a whole typical year. So this is running a relatively complex model, but you don't have to own the model. You don't have to install the model. You don't have to know really anything about the model. All you have to do is provide it with the information that it needs, and it will provide you with the answer that you want. And so that's what we have built with these web services in order to support the applications. We also open source the library. We open source the code that we use to build the framework, and that's what's being used behind api.data.gov, is the same framework that we developed at NREL for developer. This is the really interesting thing from my perspective, is this little arrow that just popped down below the rails. So in the past, everyone had to go get the data. They all went and downloaded it. They all went and got PV watts, which is the model I was just describing. They ran it on their own machine because they had to. And what we realized when we built these web services for the applications is that our analysts all over the lab started just hitting the web services. And so we've in essence made all of this data available to everyone at the lab. So you don't have 300 people downloading the same census data. You download it once, you put it in a database, and you make it available as a web service, and that's what everybody uses because it's very easy to pull it in. And so these things that we built for application development wound up being a critical part of the analysis that we do. And then this last piece is for those web visualization junkie types. So we build, and this is what I'm going to show, the last part of the presentation. I'll show some spatial temporal visualization stuff that we've done. We build these applications that actually allow users to run models, run analysis, do spatial temporal visualization, and these are all built using open source tools as well. So the whole stack, from the data being in Postgres, to the web services being in Ruby on Rails, to the interface development libraries that we use for web development, is all based on this availability of open source technology. And so if you guys are taking notes on things to go look up after the presentation, I think this is the most important slide. This is what we use. For analysis, it's mainly R and Python and the associated libraries. Postgres and PostGIS, I think it would be almost impossible for me to stress enough the importance of Postgres and PostGIS in modern geospatial analysis. This is the single most important tool that we use in the lab for spatial analysis. If you don't know how to use a database, it's not hard. And the database will install on Windows, Mac, Linux, whatever you got. It doesn't take up a lot of space. It's really easy to toss data in. And if you're not running analysis queries in Postgres, that should absolutely be something you learn to do. Take some time and figure it out while you're in school. And then when you put it on your resume, people are blown away because very few people come out of GIS and geography programs with that skill set. Quantum, obviously. We use GitHub and Linux and HDF. Those are sort of the general things that I think everybody uses. For application development, it's Ruby on Rails, NodeJS, and Geoserver, and then the other two, Python and Postgres. And then just an unbelievable amount of JavaScript libraries for visualization. Now, this is a really interesting thing, I think, and I'll try to demonstrate this in one of the demos that I'll do here in a minute. The place where you're using analysis tools and they're giving you crappy visualizations is sort of done now. And the reason is that it's very, very easy to dump data out into something that you can do great visualization with web tools. And they're really easy to use. It doesn't require a lot of programming, doesn't require a huge amount of expertise to pick them up. And you can do truly amazing visualizations with web development tools now. And I'll show you some examples of that. But the reason I'm bringing it up is not only is JavaScript a great thing to learn for data visualization, but Node.js is also becoming a real player in analysis code. And so you, in the same way that you would run Python to run GDAL or Ogre or access Postgres or run a shapefile or something like that, you can do a ton of that stuff in Node.js now. It's actually server-side JavaScript. And so libraries are being developed very rapidly to do that because the line between what you do in a web page and what you do on the server is really blurry now. And if you can do the same code in JavaScript and say, well, it's not running on the web page, I'm going to run it on the server, or, oh, the browser capacity has gone up, and so we're going to move that JavaScript to the interface for one reason or another, it's the same code. And so it really, it can be really fascinating how you sort of go across that line depending on what you want the user to do. So one silly example is like buffering a point. The point is already in the client. The client is already in the client. A lot of the other data that you want is already in the client. Why go back to the server when you can run a simple JavaScript that'll buffer a point? And so, but in order to buffer 1,000 points and then do a query and merge those together and pull another data set, you would need to run it on the server. And so we mix those things up a lot with Node.js. And we don't use it as much as others do, but that's, I think, where the industry's going in some ways. So this is your list of open source software to go have a look at for geospatial analysis. So I'm going to talk a little bit about this. I probably won't focus too much on this. I think this is really important for thinking through why the skill set is important, why you would want to learn open source software instead of traditional GIS software. The first thing is flexibility and scalability. So I take the R code that I write on my laptop, and then I run it on a little sample data set, and then I move it over to a server, and I run it on a server because I have a bigger data set, and then I run it across a bunch of servers, and then I run it on a high-performance computer on thousands of servers. And it's the same R code. And if I was doing that in MATLAB, I would be hosed. Or if I was doing that in Esri, I'd be hosed. And the reason is that you have to buy a license for every core. And you can't buy thousands of licenses. And so when you want to scale something up, open source code is really fantastic for doing that. And especially because you know how it works. It's not a black box, and you can scale it up to work on really big data sets, especially if you're going to scale it across a whole bunch of machines. Because again, I mean, we process data sets that are billions and billions of values, and you just can't do that with licensed software on one machine on one core. We experiment tremendously in what we're doing. We go back and forth between doing things in R and doing things in Python and doing things in Node and using one library and and then replace it with another library. And that's really hard to do with licensed software because they give you a few weeks to play with it. But I mean, you can go through 15 open source tools and find the right one much, much easier than you can go through 15 proprietary tools. And that's another thing that I think is very valuable as far as our ability as a team to do good analysis. I think open source helps us do that because of that reason. I would also say that one of the things I was trying to get across and may not have been incredibly clear at the beginning is when we started using web development frameworks for putting together these analysis websites, and I was talking about how the framework would define how you connected to the database and what the models look like and how the visualization talked to the model, and like the framework kind of handled a lot of that. One of the things that's really useful in that is this idea of modular design. So you build something like an application and you say, well, I've got this library that's showing me the map, right? I'm using OpenLayers and it's handling the zooming and the panning and the loading of layers. But I realized that OpenLayers isn't what I want for some reason. So I yank out OpenLayers and I put in Leaflet. Or yank out Leaflet and I put in Mapbox, right? And the ability to do that, you can only do that if you build things in a modular way. And so the thing that's fascinating about open source is it pushes you to do that, because you know in 6 months there's going to be a library that does this better than the one I'm using. So I need to build these things so that I can plug and unplug things. It's a really powerful design methodology in developing software for applications. But I would say, and we do say in the group that I work in, it's just as powerful in analysis. Do your analysis in a way that you can take the tool you're using and replace it with another tool. It compartmentalizes the work you're doing. It allows you to save in different stages easier. And it makes it far more flexible if you're going to do the same thing in a year or 2 years. Because as the technology grows, you can swap out technologies. And so the fact that we use the open source tools has put everybody into this modular development mind. And it's really helped us to do the best analysis we can with the best tools that we can. And I think that the last point probably is the most important for my team, in that I've got people on my team who are specialists in database. I've got people on my team who are specialists in web development, or the team, like the extended team. So I'm like 15 people, and I'm talking about maybe 40 or 50 people on the big team. And sometimes the thing that we're doing, we realize we're doing analysis, and the thing that really makes the analysis work is somebody who doesn't know anything about analysis comes and talks to me and says, hey, this thing happened in database land. Everything's 100 times faster now. We had no idea. We had somebody from computational sciences show us HDF5 about 3 years ago, and everything we did just orders of magnitude bigger now. We never could have done it. And the fact that we're using open source tools, and the fact that the web developers and the computational scientists and the straight up programmers and the analysts and the visualization people are all using open source tools, this cross-fertilization at the lab is incredible. And we're all learning from each other in ways that I don't think anybody expected. And so that particular piece, I think, is really fostered by open source, and we cherish it as a lab. So here's the throwing tomatoes part. So open source is a real pain in the butt. It can be. And the reason is staffing, because everyone comes out of school with proprietary software degrees, right? You've learned the tools that Oracle and Esri and all these other companies have sort of made it really easy for academic institutions to have. And so finding someone who knows how to do geospatial work, they understand the data, they understand the concepts, they really get projections and all the stuff you need to do geospatial work, and they can do analysis, and they know Esri is easy. They're everywhere. There's in every university, they're graduating folks that have had a class or two in ArcMap, right? Same thing's true for a little bit of SQL. Yeah, you guys have all used SQL in the geodatabase. You know how to run a query. And visualization in Esri, no problem. Like, people know how to make maps, even beautiful maps. But when you start to say, I want someone who gets geospatial and knows how to do analysis and actually knows how to do Postgres, like has really solved some problems in Postgres, like those people don't really exist in the academic institutions. They're not coming out, right? And the same thing's true for visualization. There are, God, when we hire, we get hundreds and hundreds of resumes from web developers. And the web developers are like, man, geospatial, that's easy. I could do that. I'm a JavaScript guy. I know how to do visualization. It's just maps, right? And they don't know squat about it, right? They can make maps that I tell them to make, but they're not coming up with good ideas because they don't really get it. Data visualization, right? They know web development. Finding someone who understands all of it, again, I don't have any, this is my only unicorn picture, but it's, they're unique. They're magical people that we really have a hard time hiring. So I think what I wanted to do until Raphael tells me I have to stop is just go through a few examples of some of the stuff that we're doing, visualization, things like that, to show you guys what I'm talking about. So I'll show spatial temporal data visualization. I'll show spatial application development. And then I don't think I'm going to show analysis just because it's kind of hard to do a demonstration of that, but I'll talk a little bit about some of the results of that. So we'll see if this poses the whole computer when I do this. So this is the first thing I wanted to show, and you guys probably have not read the Renewable Electricity Futures Study. It is, if you want to know anything about renewable energy or the current energy infrastructure, this is something that you should go and look at. It's about like this thick. You can literally beat people to death with it, but it's got, I haven't personally done that, but that's my assumption. But it's got summaries and it's got appendices that really cover the basics about how electricity works, how grids work, why renewable energy is challenging. You know, all of this stuff is really defined well in the study because they had to reference it. And so they've got these really great abstracts that cover, or not abstracts, but appendices that cover a lot of that. But the Renewable Electricity Future Study was focused on trying to figure out what the United States looked like with high renewable energy adoption in the future. So 50 years from now, if we have 80% renewables, what does that look like? How much wind does Oklahoma have? How much solar does New York State have, right? So that's what they were trying to come up with. So the problem is that they have, you guys have all done analysis, and so I think you probably understand the concept of scenarios. But you take a scenario and you say gas is going to cost this much, and oil is going to cost this much, and solar panels are going to cost that much. How much solar do we have? And then they say, what if we lowered the price of PV? How much solar do we have, right? How much wind do we have if we lower the price of PV? How much solar do we have if we raise the price of wind, right? So there's all these assumptions in the scenarios. And so in this case, there's all these scenarios, and I'll just do the drop down here, but 30, 40, 50, 60% renewable energy, right? There's something like, I forget what there is, 16 or 17 of these. And then for every single scenario, you've got capacity and generation. So I can switch from capacity to generation. You've got some number of technologies, so I can switch to hydropower, and I can show what the US looks like with hydropower. I can switch to rooftop PV, and I can show what it looks like with rooftop PV. So when you take all of these options, all the scenarios, all of the years, so there's, you know, this goes from 2010 to 2050, and you can see when I'm sort of dragging through this guy, it changes over time, right? When you look at this, this is about 50-something thousand maps that you could produce with this. So the problem with the study is you can't produce a study that's got 50,000 maps and actually show it to somebody. And so what we wanted to do is we wanted users to be able to look at this, researchers, industry, decision makers, and say, what does this scenario really mean? Like I'm flipping through the study and I say, I've got 80% renewable energy with an advanced technology increase. Okay, so if I hover over Texas in 2050, that means I've got 11,200 megawatts of rooftop PV, right? You go down, you drag through the years, and you go to 2030, and you say, what do I have in Texas in 2030, right? You can see down here in the bottom, and I'll step away for just a moment, this mix in the lower right-hand corner of the screen is really a fascinating part of the visualization, in that you can hover over this, and you can say, okay, well, this is onshore wind capacity, right? You can hover over this, and you can say, this is coal. And what happens when you go through time is you can see the relationship between wind and coal change over time as you're moving the slider around. That's really hard to get across on a static document. And that's why we do visualizations like this. All of this is done in open source tools. All of this is done using D3, which you guys have probably all heard of, to do vector presentation in the web. And I think that's all I'll say about it. These are all really interactive, right? You can click around on them and they'll jump. Like if you click in one place on one, it'll jump to another place on the other. But the whole point is to make sure that the study is easy to understand. And what this does is it provides the data in a way that's easy for people to comprehend.
Could you briefly comment on the architecture behind the application?
Sure.
So you mentioned 3D, and what else is going on here?
Yeah, so I'll correct you that it's D3, just in case people are looking it up. But it's a JavaScript library that was developed by a guy named Mike Bostock, who works for the New York Times. And when you go to the New York Times website and you see all those crazy visualizations, and he does charts and graphs and maps and all kinds of stuff on their website, he came up with his own library to do that because the libraries that existed weren't very good, right? And so the actual pieces, like the little graphs and things like that, were done with D3, but they all exist inside a framework called Backbone. And what Backbone does is you say, hey, Backbone, here's a big data set, right? And that's all in a text format called JSON. So this big chunk of data gets loaded into Backbone in these objects. And then the visualizations are able to, how to explain this? So you can say in Backbone code, you can say when the data changes, the visualizations change. The visualization chunks of code are listening to the data. And so when I go here and I click this button and I take it to onshore wind, the data changed because I set the current data visualization to wind. And when that happened, it fired an event, and all of the things that are listening to those events realized it and redrew. They went and pulled their data and redrew. And so the way that this is built, the architecture is exceedingly simple. It's a Backbone framework with JSON data and D3 JavaScript visualizations. And so, yes?
When you say data, is it raw data or processed data?
So
what I'm asking is that the maps are pre-computed maps, or they're computed on the fly as you start playing with them?
Yeah, that's a really good question. I'll take a minute just to clarify that. So in this case, they're pre-computed, because the study generated all of the results, and now we're just visualizing the results. But the difference is this doesn't have any web services, right? When you load this, it just loads the web page, and the data is all on the page, and it's all one big thing. It's not communicating back to servers. So you could literally put this on a CD and run it because it's just pre-done analysis. The alternative is to have a web server that receives a request to say, hey, I want to look at PV instead of wind, right? So you go to PV and it hits the web server, and the web server does the churning and creates the data and spits it back, and the application interprets it and shows you. So in this case, it's static. Some of the other examples I'll show are running off the web services. So this is fun to build, and we really enjoyed it. It's had a big impact. Like people, I think we have thousands of users of this. But the problem with it is that it's pretty static, right? I mean, it's really interactive. Like you can do things with it, but all you can do is look at the states, right? And you can't really get in and see some of the details. And so one of the other things I'll show you, this is our web application framework for GIS. We call it Opencart. But essentially, it's a framework for building web-based GISs. And so we have about 15 or 16 of these for the different technologies. This one's for hydrogen. And so I can turn on things like gasoline consumption and water use and stuff like that, and all the layers turn on, and you can do things like query it and change layer transparencies. And in some cases, you're going to actually change the colors of the layers. So you can say, I want to highlight a certain, class within the layer system. And I think I don't have that one turned on. But, you guys are all done GIS, right? So this is web-based GIS. It's a pretty good one, and it's slightly advanced, but that's really all it is. What we wanted to do with this, though, was to be able to demonstrate something very similar to what we do in REF. In this case, it's like REF, but focused on hydrogen. And so you can see I've got scenarios, right? So there's 3 scenarios here. And then I've got all the different things that you can show on the map. And I apologize that this is cut off on the projector. But you can say, I want to know in 2045, based on the assumptions in the scenario, how many vehicle sales I'm going to have for each of these urban areas, right? So you can go hover over the urban area, and it'll tell you what the value is. If you click on it, it actually gives you a chart of how that value changes over time. You could say, I want to see station count or production capacity, and then everything updates. And it's not just the chart, but it's the map and the chart. You can change the time series, and then it updates everything based on where you're at in time. Basically what we just showed for REF, but this is, a fully interactive map. Like I can close this, go back to my data, turn on gasoline consumption, and then look at all of the same stuff that I'm looking at with any of the base data that I want, right? So now I'm looking at the urban areas with hydrogen demand on top of whatever it was, fuel consumption, right? So we've taken that concept and moved it into like fully interactive mapping. And again, this is all using open source tools. This whole thing is built with open source tools. None of this uses anything proprietary. We have Ember is the framework that when I was talking about Backbone earlier, Ember is basically the same thing as Backbone. But all the data is stored in Postgres. We have Geoserver, which is the thing that generates the pictures of the maps. And if you click on these guys and run a query, it actually goes back to Geoserver and gives you the results. We have Ruby on Rails is the web services framework. This is all built using, trying to think of all the tools. Basically traditional JavaScript, HTML5, and Leaflet. And Leaflet is a really excellent web-based GIS component that goes into it. These things down here are built with custom JavaScript and HighCharts, which is another web library. But we didn't have to buy any of it. We don't have to license any of it. We have ultimate flexibility with it. We plug and play things in there. If we decided we wanted to get rid of Leaflet and use OpenLayers, it's all designed so that we can just rip that out and plug something else in. So again, I wanted to just demonstrate interactive REF. This is something I built not too long ago to show. This is a different problem that we're solving. So these are all the wells that we have temperatures at depth for in the United States. So again, web-based GIS, same framework, Opencart, but this is focused on geothermal. So all the data sets are going to be geothermal related, and I could pull things up and query them, but we can do that later if you have questions. The problem with this map is that, I mean, you can query it, right? But what you're looking at is chickpeas, souffle or whatever you want to call it. You can't really tell what's going on with it, and you can zoom into it, but it's very hard to do things like filter down to exactly what you want. And so what we wanted to do was provide the capability to filter these wells. Actually, I'll show you one thing first. just because you had brought up this point about static versus dynamic analysis. So what I'm doing right here is I'm drawing a box on the map. And what's happening is it's sending a query to our database, and it's running an analysis. It's a summary statistics on the data for the area of interest. And so the problem is that if you want to do geothermal exploration, there's a ton of information that you need in order to just decide if a place is worth looking at, because there's just not a lot of great geothermal or geologic data to support geothermal exploration. And so you need to know, well, who's drilled wells and what are their temperatures? You need to know, what is the land availability in the area that I'm looking at? And what we're doing is we're querying a land data set to say who owns the land in that area. You can go through and say, what are the restrictions on the land that's available in that area, right? All of the basic information you need to decide if it would be silly to do further investigation. So you can narrow it down to only the places that are most applicable to geothermal research. And all of this is hitting web services that are running this against a database, which, if you remember the diagram I showed earlier, as we're doing analysis on a daily basis, the data gets updated on a daily basis, and then these analyses run against our current databases. And so as the data changes, the users are always getting the best data we have. So that's the opposite of being static pre-run analysis.
And a backend database is Postgres.
Yes, sir. So this is how we look at the data, and there's a really specific problem that we're trying to solve with this visualization. And it's using the same tools that I was talking about earlier, Leaflet, D3, high charts, things like that. The idea is that you've got, whatever it is, like 700,000 wells. How do you find a place where you've got wells that are the right depth and the right temperature? And so what we've done is we put a visualization together that allows you to do that. So one of the things that we're trying to do is these shallow, low temperature wells for certain geothermal technologies. And so you can click on one of the states, and it'll show you the distribution of wells for Pennsylvania. This always takes a minute to run the first time. You can also, instead of looking at depth, you can look at minimum borehole temperature, maximum borehole temperature, all of the values that are associated with the wells. You can filter the map on it dynamically, just like that, right? It updates. And these are all pulling off of a server as well. So what we're looking at right now is how deep is the deepest well. And then what you can do is you can actually change these filters, and you can say, I'm only interested in 50 to 150 feet, right? So you grab the slider, you draw it down, and the map updates. We're going to take this down. Sorry, that was temperature. I'm going to go down to 3,000 feet. Right, so now you see what the US looks like between those two filters. And as you're zooming in, it updates to show you all the counties with those filters. And you guys can think about this as the modifiable aerial unit problem, where you're doing like dynamic aggregation and things like that. Those are things we think about in trying to decide how we aggregate. Sorry, I zoomed in too much and I actually got the actual wells. And it screwed up my whole point. Sorry. So you zoom in and you can hover over these counties, and then you can click on a county and you can see the distribution for the county, right? Between these two filters. And so you can say, oh, well, this is a county that's really got what I'm looking for. And then you zoom into the county and you get the actual wells themselves. And I got to find a place where there's wells. Yeah, so then you can see these guys, and you can click on one of them, and it's just saying, hey, man, I'm going to give you a chart. But then as you move the map around, all of these things update, right? The legend updates, the chart updates. So again, these are data sets that are hard to get your head around unless you have software and knowledge, right? So you guys all have ArcMap and you know how to use it, but a whole lot of people don't. And so what this does is it lets them play with the data to say, okay, well, this is the place where I've got all these wells of interest. And you can take that and you can show your congressman. You can take that and you can show your state representative. You can clip this and make a PowerPoint and say, why aren't we doing low temperature geothermal, right? So this provides that power to folks that were interested in renewable energy but don't necessarily have all the analysis tools or the money to sort of do that themselves. And I'm going to keep, Raphael, like I told you, I'm going to keep showing stuff so you just point at me and say no. Yeah. So this is if I can click on it, this is a fun example because this is for the Philippines. This is our wind application. So and I'm going to demonstrate basically how we're using open source tools to solve a completely different problem, which is we have these enormous data sets. In this case, it's 4.5 terabytes of wind data here. So if you zoom into this guy, you can see that these are all points, right? These are all individually modeled points where we have estimated what a time series of wind data is. But each of these points has a year's worth of data at an hourly level. And so we're talking about this enormous data set, and you can't just get it, right? And so what this application does is it lets you say, I'm really interested in getting data for just this part, because that's where I'm thinking about putting a wind farm, right? And so you run a query, and it goes and gets you all the points, and then you go click download data, and you can download only the attributes you want for only the place you want, right? So you have access to a 4.5 terabyte data set, but all you're going to get is like a couple gig, maybe a couple hundred gig, right? So as you're selecting attributes, you hit your capacity, right? So I selected an area that was big enough where I selected one attribute, and that's all I can download. And that's going to go up as the technology gets better. But all this is done using HDF5 files with Ruby on Rails web services and a thing called Globus Connect, which actually isn't open source, but they do have open source toolkit for developing your own tools that use Globus to deal with data transfer, right? So what it does is it parallelizes the downloads and then puts them all together on your end so you can download bigger data sets. So again, the problem that this solves is how do you provide access to an enormous data set? And again, we solve the problem with mostly open source tools. I'm going to talk about two more things. Oh yeah, sorry.
Those points or dots, are they tiles or they're actually interactive?
Yeah, so that's a good question. Sure, yeah. The question was, I'm just going to bring up the points. The question was whether the points on this map are interactive or tiles. And the answer is that these are tiles, right? So the interactive part is the drawing of the box, but you can't really have whatever it is, hundreds of thousands of interactive points because the browser can't handle it, which is the same reason why when we were looking at Geothermal Prospector, you didn't get to see the wells until you zoomed in because we can't show 700,000 interactive points. We have to show 50 interactive states and then a couple hundred interactive counties and then a couple hundred interactive points. So this is something that John actually did most of, and I can't get this thing out of my way. Here we go. So this is given the other things that I've showed you, this is much, much, much simpler, right? And it's intended to be. The idea here is that this is an interactive map, so you can click on Texas, you can click on Arizona and New Mexico, and you can see these charts updating, and then you can take this and you can sort of slide through time, and you can see the map changing, and then these values down here for the market share. You can switch which value you're looking at. This does not require a web server, and you can actually generate this from R. And so the idea is that you're running R, right? I'm sure you guys are all running R all the time. But you're running whatever you're running, right? MATLAB, any software that you're running. The idea is that the output from that software can be made into a format that works in the web. And so in this case, and I don't know if I can, I'll try to make this bigger. Yeah, maybe I can't. What I'm going to do is I'm going to change this from blue to orange. Oranges. And you just select it all, and you run it, and you go back to your web browser, and you hit reload, and it's updated, right? And so the idea is that you're not limited to the visualization that your software offers you. If you can do a little bit of web development, and man, the tutorials on this stuff are crazy. If you just look around online, like you can literally go from I've never seen it before to I have a map and I can click on it and stuff happens in like a day or two, right? It's well worth investigating because the visualization does what you want. What I want to do is I want to run it over and over again and I want to compare two states, right? And it comes up exactly the way you want it to look. And it's ready for you to take a screen capture of and stick into a report or something like that. Just a little bit of web development using open source tools that you don't have to pay for, and your software can actually produce data that look the way you want, right? So John and I came up with this idea for a team of people that were running analysis for about a year, and they all wanted to be able to see each other's results in the same way. So they all have this thing where you run it and the output goes in a certain place, and then everyone can kind of see everyone else's data in a way that they're familiar with. This is something that John built on his own. It's growing up so fast. It's like, he can't believe it. So this idea is that people want to be able to see what's happening in your work, but we keep sending people these spreadsheets. It's like, hey, here's our data. Person who doesn't understand analysis and hired me to do it. Here's my spreadsheet that you don't understand, right? So what we tried to do in this case, what this is showing is different states, in order to meet their renewable energy portfolio standards, which is I'm supposed to have a certain amount of solar, they'll actually import solar energy from another state to meet that standard, right? And so if you go click on one of these guys, Pennsylvania, you can see the statistics about Pennsylvania, and then the map shows you how much energy Pennsylvania is getting from other states to meet the standard, right? And whatever state you click on, it's really interesting because you can go back and forth between Ohio and Illinois, or Ohio and Pennsylvania, and they're importing from each other, which is fun to meet this. I don't know. But the idea is that this is kind of hard to get your head around a little bit, and it looks a little weird in a spreadsheet. But if you want, and this is just fun to show in it, and I'm so glad you brought up the point you did earlier, because it really, this is a single file, index.html, right? You put this in an email and you send it to somebody, and when they open it and double click on it, it looks like this. They don't have to download anything. They don't have to hit any web services. You could literally stick it on a USB drive and give it to people at a conference, and what they're seeing is your data, but they're seeing it in a way that allows them to really understand it. And that's, again, I talk a lot about visualization because it's one of the things I do a lot of, but this is sort of the take-home point is there's so much misinformation out there about energy and renewable energy and energy policy and things like that. What we're trying to do is make sure the data we deliver is super easy to understand, right? And this is the way we're focused on doing it, is making sure we're not handing somebody a spreadsheet. You can download the spreadsheet from the site, right? But this shows you what it means in a way that allows us to present it in the way that we think it's easiest to understand. So I think that's where I'll stop and then answer questions if there's time.
Can I make a quick question? I'm going to see up there for the recording.
Yeah.
For the people. Just a quick question. You mentioned for the last two applications that John did it. So if you could comment, who is John, and you, John, if you can comment, how long did it take you to do this and learn it?
Yeah, why don't you come up and talk about it, John?
Both.
Yeah. So John Duckworth is my intern. I'll tell you the side. I think John Duckworth has a whole other life here that I don't know. But so John came to us from CU in Boulder doing civil engineering. Yeah, and
CU Denver.
Yeah, and CU Denver, and wanted to learn about visualizing spatial temporal data on the web, and that's what he's been doing for us. And so for the last 6 months.
Yeah, since June, I guess so.
Yeah, it's almost a year.
Yeah.
He's been working on projects just like this. So standalone visualizations, helping with some of the bigger applications, things like that. You want to maybe talk a little bit about that?
Yeah, sure. Yeah, and so actually, Raphael's WebGIS class was the first exposure, I guess about a year and a half ago, that I had to any of these kind of web technologies. And I think the semester before that was the first exposure that I had to things like Postgres and some of those technologies. So what Dan said earlier about being able to pick some of this stuff up really quickly, that's one of the nice things about things like Postgres and the JavaScript libraries. There are a ton of really good tutorials out there. It's pretty easy to find documentation, and it's pretty easy to find other people's code that you can kind of take and look at and say, oh, that pretty much does what I want to do, and then alter it a little bit and turn it into something that's your own too. So yeah, so I feel like it's been pretty easy learning process.
And I wanted to ask that question because at some point in your slides you mentioned working with open source can be troublesome. So what can be common to you?
Yeah, so it's really, really easy to pick it up, and it's really hard to get really good at it, is what it boils down to. I mean, there's enough examples out there to where if you wanted to do something like this, it wouldn't take you that long to figure it out, right? But being able to come up with this, looking at data, is the real challenge. And so it's finding someone who, so it's interesting, and I'm more familiar with this from the perspective of hiring application developers. And so what you get when you hire application developers is you get someone who comes in and says, I really know the back end. I know web services. I don't know how to make things pretty. It's almost like a badge of honor that you don't mess with the interface, right? That's somebody else's job. That's the designer's job. Like, I'm really good at making things fast. And you get an interface developer, and they're like, man, I can make things look great, but I don't do web services. And so what's really special is someone who knows how to do both, right? So John really knows spatial analysis, and he's got training in it. He's really good at it. He knows how to think that way. And now what he's learning is how to do spatial temporal visualization using JavaScript. And developing those tools is why he's going to quit in a year and go make a whole bunch of money somewhere else, because it's hard to find people who combine those things, right? So, but I guess the point that I'm making is they're relatively easy skills to pick up. And if you've got a good design sense or you've got a good programming sense, you can actually spend some time and develop those capabilities. It's just hard to find somebody who already knows them. So we tend to grow people to do that. Anybody else have any questions? God, I almost want to go back to my man and his C code slide, because the way that it's been done. Oh, I'm sorry. The question was, how do you deal with big data sets in Python because you run into memory issues when you try to open them? Yeah. And so the answer is, I guess there's kind of two parts to it. And I'm not a computer scientist by trade or even really training. But what we've done for certain kinds of math is you basically split the data out, right? So the guy in his C code earlier, those data sets, terabytes of data in hundreds of thousands of CSV or text files, right? So they would open up 1,000 at a time and do a process and open up the next 1,000 of the process. So that's really challenging when you're doing things like matrix manipulation, or you're doing PCA or something like that, where you have to process the whole matrix. And so the answer to that is there's software out there that you can use to do that. And I know it exists in Python, but I don't know what it's called. But you can use Spark, or you can use PGDB in R. And what those allow you to do is they allow you to do full matrix operations over a distributed system. And so it's not that the math is impossible, it's just that it's hard to keep track of it all, to do those complex matrix operations. And so what those libraries do is they allow you to distribute complex problems over multiple computers. And that way you can solve some of the memory limitations. But if you have a laptop and you're running a huge data set and you want to do a matrix transformation or something like that, and I can't magically solve it. But what we do is we distribute it, and we use libraries that know how to distribute it to solve that problem. But that's a fun problem. One of the things I realized working at the labs is that you can walk down the hall and talk to a world-class statistician or a world-class computer scientist, and they just are there to help you. They're doing their work, and they come ask you spatial questions and things like that. But that's what I do, is when I run into a problem like that I can't solve, I go sit down with a computer scientist and I say, you guys are studying this. How do we solve it? And you've got a great excuse to do that here. So Python is surprisingly well adopted in computational sciences, and R and Python both are surprisingly well adopted in applied math and in some statistics departments. So.
NREL have this library, right? Those are very good libraries for art. Those are not GIS specific libraries. It's really difficult to adopt those libraries. Setting a project for it and make it possible to use those things in the environment.
Yeah, so I will summarize your question as saying there are multiple simulation and modeling libraries that NREL's developed. Energy Plus was one. I forget the other one. Radiance. And are they available in a way that makes them easy to apply in 3D environment or spatial environment? And I think the answer is that some of them are and some of them aren't. So PV Watts is one that I mentioned that we do have available as web services, and that'll give you the output of a PV system given certain characteristics. But there are... So one of the challenges we have with the libraries and modeling algorithms that are developed in NREL, some of them are really complicated. Some of them require specialized optimization software that's licensed. Some of them require data sets that we're not allowed to share. And so it's actually kind of hard to make some of those available as web services. And that's, I think, the case with the ones you're talking about. They just don't really run as a web service because there's so many parameters that go into running it. Another issue is we're doing everything that we can to make sure that the money that we spend is spent wisely. And there's a lot of checks and balances when you propose to the government and say, hey, Department of Energy, give me some money to do this thing. They go through, billions of dollars worth of proposals and give millions of dollars worth of money, right? And so in general, things like Energy Plus, which seems well used in certain communities, but isn't something that's got like millions of users, taking that and turning it into web service is expensive, and it isn't always cost effective.
Any other questions?
Yeah.
And I will go and say that quickly. So, I mean, you can see why we have done in the advisory board for the new masters in geography and applied geospatial science and technology. So my question is this: you mentioned at the beginning of your presentation that it is very hard to find these unicorns.
Yeah.
So students come out of degrees with all the things that you see are necessary. So you could briefly comment how we would look at a program that would create these unicorns. Because here we have Farnoosh, a professor in computer science, and that's something that, him and his students will be better prepared for certain things, and the students in geography or architecture and planning will be for others. So what can you tell us about that?
Yeah, I thought you did it because you enjoyed the abuse. I'm actually really looking forward to those conversations because So I came to a master's program where none of this stuff was taught. I actually went to, I took a whole bunch of classes at CU Boulder just to brush up on my spatial statistics and things like that. And I was fascinated that they were using R for all of that. But nobody teaches Postgres there. Nobody teaches this. And so I would think that, I mean, we need to have discussions about what you guys really want to try to accomplish. But from my perspective, if I was just going to design a program, there would be geospatial analysis would be taught in Python. That's how it would be taught. It would not be taught in Esri at all. And it would be taught using a combination of Python and Postgres. And then visualization would be done either highly specialized design, like using Adobe Illustrator and those sorts of software, or we'd be talking about how you generically use web tools to visualize data so that no matter what the data, no matter what you're doing, it comes out in a way that you can actually use in visualization. So I think database, object-oriented programming, specifically focused on Python because it's a great language for spatial analysis. And then I think that the piece that's missing from most geography programs in the United States is you can push a button and you can interpolate between values, but how do you do that? Like, what's the math behind that? How do you do spatial statistical analysis? And I feel like getting an understanding of that is really hard. And geography departments, I think, are sometimes intimidated because how are we going to take these folks who are, sort of a liberal arts kind of a background and then put them in a very complex math background? But the alternative to that is, we have students that know how to push buttons and don't really know why to push those buttons. And so I think that integrating a solid statistics background, and or a solid programming background and or a solid design background, I think the program should have those branches. And like you can take one or the other or both, but that gives you the foundation you need to be, it's hard to talk about because in some ways I feel negatively about geography programs teaching GIS because, man, you look at AutoCAD. You used to have to be really good at Architect to use AutoCAD. You really had to know what you were doing. And now AutoCAD is a commodity, right? People come out of school, they know how to use AutoCAD, and GIS is headed in the same direction. There's a lot of folks that just need you to make maps, right? And if you don't know how to do anything other than make maps, then that's what the degree gets you. And I think that knowing these other things is what puts you in a position where you're going to be doing research, you're going to be doing analysis, you're going to be doing problem solving. And that's what takes you a step further, where that's why people want you, is because you can do that problem solving. So it's well worth taking the time to learn those skills.
Got a comment from a question from a remote participant. That you mentioned that programming is something I can pick up. Would you say the same for statistical modeling, or would my time be better spent getting a master's in that field instead?
Man, that's a great question. Yeah, so I'm sorry, did that pick up from your end, or should I repeat it? Yeah, so the question was, you can pick up programming relatively easily, which I will stand by that statement, but can you also pick up statistical modeling as easily? And I think that I'll say two things about it. The first one is I'll say it depends. If you have a really strong math background and you really just need to take that next step into statistical analysis or complex data modeling, I feel like you probably can. You really know your calculus, you really know differential equations, you really know modeling, and you want to learn some statistics, I think you can catch up. But if you don't have that background, I think you probably are better off having someone teach that to you. And the reason is that you can go get a book and you can read all the equations, but what you get out of a statistics program is somebody giving you lots and lots and lots of examples about why the statistics work, why they don't work, where to apply them, where not to apply them. What when you look at the output of a t-test or a p-test or something like that, what is it really telling you and what isn't it telling you? And I think that most books don't tell you that. And you just flip through it and it's like, here's what it is. And if you don't know the calculus, then you don't know how it was calculated. So I feel like, not having the best math background, that's why I went back to school, was to go and make sure I understood that stuff very, very well and at a depth that would help me use it. With programming, I feel like it's really about running your own examples, right? You need to solve a problem and you need to use the code to do that. When you start to get into object-oriented programming and things like that, I think it can get a little more complex. And if you're going to use it for big analysis projects, that can be hard to pick up on your own. But I think that's, I've seen people grow and do that. I haven't in my life seen a lot of people grow and do that with something like statistical modeling.
Any other questions or comments?
Yeah, someone else just commented that you're right on with with the Esri and how using Esri now common skills, like knowing how to use Excel, Word, at the bare minimum.
You know, I'd say something else. So the comment was just a confirmation of my awesomeness. No, it was just saying that, you know, Esri becoming a commodity skill set is something that we're seeing. But I would say the other end of that is really, as I've been fascinated by, so statistical analysis, like geospatial statistical analysis, is just part of statistics now. You know, spatial data in a database is just part of database now. So if you go get a degree, you know, and you're learning about databases, they're going to teach you that, right? And so some of the really hard things that we do as geographers and people who understand spatial data and spatial analysis, we have people that are competing for that work that don't have a background in geography at all, but they're making assumptions that they can do it. And, you know, these are not people these are very smart people who do really hard things, but that doesn't mean that they really understand, you know, I mentioned before, the modifiable aerial unit problem, right? Oh, well, we'll just aggregate it. Well, that doesn't really work, but it seems like it works, right? And from a database perspective where you're running query after query, a lot of that's really straightforward, but a lot of the spatial issues aren't. And so I feel like being on the same field of play where you understand the vocabulary and you can talk to folks that are doing that helps tremendously in being able to develop those relationships and solve problems together, utilizing the dramatic skill that someone who has been doing database for 20 years brings to the table, and you'll be bringing to the table what the fundamentals of the analysis are. But you got to be able to speak the language, or else you can't really make that connection as easily.
Well, thank you very much. Thanks so much, Dan, for being here. And the recording, again, will be posted in about a week on our website. And thank you for coming and for your attention.
Dan, you can see the comment that they wrote